Good evening, everyone, and welcome to the Fall 2024 Vernon Lecture. This is sponsored by Mount Cuba Observatory and the Mount Cuba Foundation, and tonight we're very happy to welcome Dr. Alex Filippenko. And you might not remember, but this is his second visit here. He was here in 2009. He got his PhD in 1984 from Caltech. He's been on the Berkeley faculty since 1986. His research focuses mostly on black holes, gamma ray bursts, and the expansion of the universe. And we're also very honored because he was on both teams that use observations to find the expansion of the universe and the existence of dark energy. And that work resulted in the 2011 Nobel Prize. So we're very glad to welcome Dr. Filippenko.
Thank you so much. Thank you for that warm introduction. It's certainly a great pleasure to be here again. Yeah, indeed, when I received the invitation to come, the name, rang a bell, in part because the Mount Cuba Foundation has been kind enough to support various instruments that have been made for the Keck Observatory, the twin 10-meter telescopes in Hawaii, and we are very grateful for those donations. But I also sort of thought, well, didn't I speak here some time ago? And sure enough, on the web, I found this, November 7th, 2009. So it's been 15 years, and there I discussed the research that led to the discovery of the accelerating expansion of the universe. And just, to be absolutely accurate here, though the Nobel Prize is given for a certain discovery, in this case, the accelerating expansion of the universe, technically, the prize is given to, at most, 3 people who are usually the leaders of the teams, and I was not the leader of either team, so I technically did not win the Nobel Prize, but nevertheless, the team leaders understood that without the rest of us working in the trenches, the discovery would not have been made, so they spent a significant fraction of their prize money flying the rest of us out to participate in Nobel Week, December of 2011, and that was really a lot of fun. But the true prize was in helping make the discovery. Never as a kid did I think that I would be involved in such an important breakthrough. And it certainly was a lot of fun. But I think that's what I discussed back then because the title of my talk was Dark Energy and the Runaway Universe. I'm not sure if it was in this auditorium. Was it in? It was. Oh, okay. Well, it's been 15 years. Can't say that it looks familiar, but it's been 15 years. The other thing I thought I'd mention is that, of course, unfortunately, I have some competition tonight, right? In 1 hour and 25 minutes, the debate starts. And I'm sure quite a few of you would like to see it in real time, live, as would I, but I will stay for Q&A for as long as it takes, but I won't drone on and on. I'll try to keep the lecture reasonably short. There have been times where I've droned on and on until midnight if the audience wants me to stay that long, but I realize that there is this competition tonight. That's unfortunate, but that's the way it goes. Okay, well, the James Webb Space Telescope was launched on Christmas Day, 2021, after more than a decade delay, but sometimes good things are worth waiting for. Had it been launched when originally planned, it simply would not have worked. And in fact, it's working very, very well, better than anticipated, actually. And of course, there are the inevitable comparisons with the Hubble Space Telescope, which has served us well for more than 3 decades now, launched in 1990. And I'm a Hubble hugger. I still use the Hubble Space Telescope. I also use the Webb now. But from the Hubble's perspective, I can understand how its feelings might be hurt a little bit. There's this new kid on the block. He thinks he's the center of the universe. I hate him, Hubble says, because of course, most of the headlines now are about the results from the Webb telescope. But the Hubble still is very, very important. Let's make some of the comparisons. First of all, the Webb has a much bigger mirror than the Hubble. And the mirror is like a gigantic eyeball. It's like a giant pupil that collects light, starlight that's raining down upon us. And indeed, your pupils dilate at night so as to collect more light so you can see fainter objects. There's also a change from the cones, which detect colors but are not very sensitive, to the rods, which detect black and white, shades of gray, but are more sensitive. But forgetting about that, the pupil dilates in order to collect more light. So the Webb has a factor of 6 bigger collecting area than the Hubble, because it's got this 6.5 meter diameter mirror versus only about 2.4 meters. And so it collects light about 6 times faster than the Hubble. It also has this gold coating, which is important for the type of light that the Webb collects. And that type of light is not visible and ultraviolet, which are the kinds of light that the Hubble detects, but rather primarily the infrared and a little bit of the red, a little bit of the visible light. So ultraviolet is shorter wavelengths of light than violet. Comes from hot objects, very energetic phenomena, and visible light as well. Our sun shines a lot in visible light. But there's also the infrared, and that's a different part of what we call the electromagnetic spectrum. It's all electromagnetic waves. I won't get into the weeds too much. It's the same qualitative phenomenon, but with quantitatively different wavelengths. And infrared is often called heat radiation. It's what you feel when warmed by the coals of a fire. You see the orange and red parts of the electromagnetic spectrum, but the coals emit much more of their light in the infrared, and that's what warms us. And so that's what we call heat radiation. And indeed, the gold cover of the mirrors reflects infrared very well, and that's what the Webb is tuned to see, okay? So observing at these infrared or heat wavelengths can tell us different things about the celestial objects that we are studying, different from what visible light and ultraviolet light can give us. And so I get annoyed when the media, and even more annoyed when my colleagues, only some of them, call the Webb a successor to the Hubble. No, it complements the Hubble. The Hubble is still useful. It gives us information at visible and ultraviolet wavelengths. The Webb gives us information about infrared wavelengths. Where's Federica, one of my colleagues? Federica, you don't call it a successor, right? At least I hope not. But some of our colleagues do. And they talk to the press, and it's not the press's fault then when astronomers say that it's the successor to the Hubble. It is not the successor to the Hubble. It is complementary to the Hubble. And I am both a Hubble hugger and a Webb hugger. So please don't call it a successor. Another comparison is that the Hubble is in what's called low Earth orbit, only a few hundred miles up. That's really great because the Hubble could be and was serviced by astronauts aboard the space shuttle for much of the first 30 years. It's been about a decade since the last servicing mission. But every 4 or 5 years, astronauts could go up there and replace aging equipment with better new technology, or replace the gyroscopes, which are used to orient and to point the telescope. That's great. It was serviceable, all right? If there were a lot of money in NASA's hands, it still would be serviceable. But the problem with the infrared is that the sun emits quite a bit of infrared light, and that would get reflected by Earth. And moreover, Earth is warm, and it puts out infrared light, just like we are warm and we put out infrared light. And that infrared light would swamp the faint infrared signals that we are trying to get from distant celestial objects. And you might say, well, reflected visible light would swamp the visible light signals as well. But there's a trick. We only use the Hubble over roughly half its orbit when it's on the dark side of Earth, when it's nighttime, all right? But even during nighttime, the warm Earth radiates infrared, and so there is no infrared nighttime for a low Earth orbit satellite like this. So you've got to put the telescope somewhere far away where it does not have Earth's reflected light and heat. And in the case of the Webb, it's placed at what's called the L2, the second Lagrange point, which is about 4 times farther from Earth than the moon is, so about 1 million miles, something like that. And this has the interesting property that an object placed there is reasonably stable. It stays there for quite a while. Gradually, it'll try to drift away, but if you have some little thrusters, you can shepherd it back into place. It's a semi-stable location in space, whereas typical places in space are not stable. Objects will just go zipping around to other locations. But placed here, a satellite will basically remain there. And it'll remain collinear in a straight line with Earth and the Sun, because in fact, this L2 point orbits the Sun in exactly 1 year, as does the Earth. Now you might say, why is all that useful? Does it make the spacecraft cold? No, being at the L2 point alone does not make it cold, because look, Earth is 150 million kilometers from the Sun. L2 is only 1% farther from the Sun than Earth is. So if Earth is warm, an object at the L2 point will be warm as well, unless you do something to cool it down. All right? So how do we keep the telescope cool? Well, there are these sheets that are about the size of a football field. And they're made out of very thin stuff, like bedspreads, but it's a different material. And with 5 of them, it's amazingly effective. I didn't believe this when I first heard about it, that engineers were planning to do this. But on the sun-facing side, the temperature might be 260 degrees Fahrenheit. And after you're 5 sheets over, and on the telescope side, you're at negative 390 Fahrenheit for a differential of 650 Fahrenheit degrees caused by these bed sheets. It's astonishing. All right? And by the way, you need these low temperatures so that the telescope itself does not emit so much infrared light that it would swamp the signal that you were trying to study. So how do they do this? Well, it's some sort of weird stuff, polyimide film, the Kapton E variety. There's going to be a quiz afterwards. No, don't worry about it. It's very thin, 1/20th of a millimeter thick to even 1/40th of a millimeter thick, with aluminum and doped silicon coatings, yada, yada, yada. But the point is, it reflects most of the incident sunlight, and that which makes it through bounces around between the first and second sheet and eventually makes it out to the sides. And that which makes it through the second sheet bounces around between the second and third and goes out the sides. And the radiation then, some of which a smaller and smaller fraction, makes it to the fourth or to the third gap and then the fourth gap. And so by the time you get to the space beyond the 5th sheet, there's essentially no radiation going through. And so the telescope is kept very, very cold. It's brilliant how this was all done. Well, you can't fit these football fields or even the mirror in any conventional rocket. There are no rockets that are football field in diameter, so they had to compress this thing, fold it up into something like a tin can the size of a school bus. And there was this very complicated unfolding sequence with 344 potential single-point failures. Now, suppose each of them has a 99% chance of working correctly. That sounds pretty good to me, but they're all independent events, and if any one of them goes wrong, the whole thing doesn't work. So I was a pessimist. I gave this thing a 3% chance of working before it was launched, because 0.99 to the 344th power is 3%. I'm glad I was wrong. It works beautifully. It works better than the original specifications. But they had to unroll these sheets and have little levers that would get them unstuck if they got stuck at certain places, which they did. And then there was this unfolding of this triptych mirror, which you're seeing here. And then, lining up the different 18 segments so they're all looking at the same part of the sky. It was absolutely astonishing, but it worked. That's good, because the Webb cost $10 billion, and unlike the Hubble, which was flawed in the shape of the primary mirror, well, astronauts could visit it and put in corrective, lenses, although it was all done with mirrors and stuff. But the Webb, being so far away, is not easily visited, and so it was sort of just, it either works or it doesn't work. And I'm glad it works. So here's the very cold observing side, and here's the sun-facing side, which first of all has some solar panels. That's great, because the whole spacecraft is powered by sunlight. And secondly, there's a little antenna here with which the telescope communicates with Earth. So signals are sent, hey, point at such and such a galaxy, and data are taken, and then those data are sent back by radio signals. So you needed that antenna. But if the satellite were exactly at the L2 point, collinear with Earth and the sun, then Earth would block or eclipse most of the sun. Not all of it. It would be what's called an annular eclipse, an annulus left over. So you wouldn't get power coming to the satellite, and also looking back toward Earth, trying to get the radio signals, well, you'd be kind of swamped by the radio emission produced by the sun. The sun emits primarily at visible wavelengths and the infrared, but it also emits at radio wavelengths, and that would swamp the radio signals that we're trying to get from Earth. So you don't want to be exactly collinear. So what do? Well, there's another Lagrange point, L1, where we've had spacecraft for decades now, in particular SOHO, the Solar and Heliospheric Observatory, which monitors the sun 24/7. And you notice that SOHO goes through these things called a halo orbit. It naturally does this around the L1 point. The physics and mathematics of that is not entirely obvious. I've never fully convinced myself from first principles that it works, but it does work. The NASA engineers figured it out. So there's a similar halo orbit around the L2 point. And so the spacecraft, the telescope, is not exactly collinear with the sun and Earth. That means Earth doesn't partly block the sun, and it also means that looking toward Earth, we're not looking toward the sun, and we can get the faint radio signals from Earth. So this is all a very good thing. All right. The first images that came out, once they aligned the 18 segments, looked like this. And you might say ooh and ah. I say ooh and ah because there are all these galaxies, giant collections of billions of stars back here. But you might say ooh and ah because of this amazing pattern here. No, instead you should say yuck. Remember that? Yuck. This is what's called the diffraction pattern produced by a bright star. What's it caused by? Well, the wave nature of light makes it bend around edges like this of the hexagonal segments and produce these main spikes here. The hexagon does that, one in each direction for each side here. And then the struts holding up the secondary mirror, they produce a diffraction pattern as well. And by the way, you need a secondary mirror because starlight comes in, bounces off the primary, goes up to the secondary, bounces through a hole in the primary, and the instruments are on the back side. So the struts produce a diffraction pattern as well, this bending of light. Two of the struts could be aligned parallel to the edges of the hexagons, but a triangle being different from a hexagon made it impossible to align the third strut with the edges. And so you get a fainter diffraction pattern here from that third misaligned strut. There's nothing we can do about that other than dealing with it in the software, in the analysis of the data. Or if you wanted to study that little galaxy there, you wait a while, this whole pattern rotates, and that means this spike won't contaminate that galaxy. But nevertheless, these spikes from bright stars are a major pain in the rear that we have to deal with. So when I show you the pretty pictures taken by the Webb, and you see these things here, you should ooh and ah at the things that are important and say yuck at these stars here, okay? The other thing to keep in mind is that in all the pictures I show you, and in all the pictures in newspapers and magazines, what you're seeing is a visible light representation of intrinsically infrared wavelengths, wavelengths that our eyes and brain do not register. So what's normally done is long infrared wavelengths are assigned in a color palette to red, R. Medium infrared wavelengths are assigned to G, green, and short infrared wavelengths are assigned to B, blue. So you get an RGB image or a representation of something that is intrinsically infrared. That's something that's not usually discussed in the pictures that are shown by the press. But all of the pictures that I show will be of that sort. Why view the infrared? Well, first of all, different wavelengths reveal different physical processes. And let me show you an example of that, where we're looking at a certain region of the sky, about 1 million light years on a side, and a light year is the distance light travels in a year. It's very far, 6 million miles, okay? And we're showing a cluster of galaxies here, about 1 million light years on a side, all right? Now, galaxies are giant collections of hundreds of millions or billions of stars, and here's a cluster of those galaxies. And what you see at visible wavelengths is basically the stars. So you say, okay, there's a bunch of stars there. But now if you look at radio wavelengths, and again, this is a visible light representation of radio wavelengths, which you could hear with your radio receiver if you had it tuned to this object, but you can't see them. And here the different colors represent not different wavelengths, but different brightnesses of the radio waves. Anyway, you see something very different than you did at visible wavelengths. You see a little dot there that probably corresponds to the middle of that galaxy, but you see these weird lobes and stuff. Without getting into the weeds, these are caused by rapidly moving electrons zipping around in magnetic fields. The point is, not stars. You've learned something new that you wouldn't have guessed looking at just the starlight. Conversely, looking at X-rays, and again, this is a visible light representation where the brightness indicates the color indicates the brightness of the X-rays, not their wavelength. Bright ones are in the middle there, and they're roughly centered on that galaxy, but there's this diffuse hot gas permeating that cluster of galaxies that you wouldn't have guessed was there if you had only looked at the visible wavelengths, right? So it stands to reason that if you look in the infrared, you'll learn something new as well. Okay? So far, so good. All right. Here's another reason to view the infrared. You can study how galaxies evolve. How do these things that are these collections of billions of stars, 100,000 light years across, how do they form? How do they evolve with time? How did our Milky Way galaxy form? We think our Milky Way, if we could see it from the outside, looks a lot like this galaxy. This is not a picture of our Milky Way from the outside. If anyone has a picture of the Milky Way that looks like this, come up to me afterward. I'd like to purchase usage rights from you. But we're like the mouse in the maze, right? It's hard to tell for the mouse, I would think, exactly what the maze looks like, but from above, it's easy to tell. So in some ways, we know the structure of other galaxies better than we know our own. But how do they form? How do they evolve with time? Well, you can look at what typical galaxies appeared to look like long ago and compare with them with their appearance now. And you look at the universe as it was long ago by looking progressively farther in distance and thus further back into the past. All right, because light doesn't travel infinitely fast, but rather at a fast but finite speed. So if you're looking at galaxies that are 1 billion or 4 billion or 9 billion light years away, you're seeing them as they were 1, 4, 9 billion years ago, and you can make some assumptions about populations of galaxies. This kind of galaxy evolved into that kind of galaxy and so on and so forth. It's not easy, but that's how you do it. However, the universe is expanding, okay? And that was the subject of my talk, indeed, the accelerating expansion 15 years ago. And that expansion of space stretches optical and ultraviolet light that the stars in the galaxy emitted long ago and makes them appear as infrared light by the time they reach us. Because although Earth and galaxies are not stretching and your body isn't stretching, despite what you might think after a big dinner, that's your fault, not the universe's fault. We're tied down, in our case by electromagnetic forces or gravity holding us to Earth or gravity holding galaxies together. But in the empty space between galaxies and clusters of galaxies, there's nothing to hold things together. And so the space expands and the light expands with it. And so intrinsically optical and ultraviolet waves become infrared. And so the Hubble can't see them. So to study the first galaxies to have formed, you have to look at infrared wavelengths. And indeed, then, a little over 2 years ago, at NASA's first press release, they showed this stunning image. And it is truly stunning. You might say, wow, look at all these things. But instead, for those things, you should say what? Yuck. That's right. Maybe they are interesting stars. Maybe they have some interesting planets orbiting them or something like that. But that's not the purpose of this picture. The purpose of this picture was to show lots of galaxies, and these yucky things, stars in our own galaxy, just get in the way. So first and foremost, the Webb confirms something that the Hubble had already told us, and that is that there are hundreds of billions, even up to 1 trillion galaxies within the realm of today's biggest telescopes throughout the sky. This is a tiny fraction of the sky. This is like a grain of sand held at arm's length. Imagine how small that looks. Yet here you can see literally thousands of galaxies. I could count them. 1, 2, 3, 4, 5. I could use up my time before the debate counting galaxies. This would be pretty boring for you. But you know what? It's a rather cushy job. They pay me to sit around and count galaxies. What could get better? I see some youngsters here. Consider a career in astrophysics. You get paid to sit around and count galaxies. Anyway, so it's not that the Webb rewrote the textbooks. We already knew that there were hundreds of billions, and indeed, the number is now up to 1 trillion, but truth be told, it's because a lot of the little tiny galaxies Webb sees are fragments of galaxies which later coalesced into bigger things like the Milky Way. But it did, reaffirm that there are lots of galaxies out there, and some of them are so faint and tiny and look like they're so far away that maybe we're looking to the very beginning of time almost, to the formation of the first galaxies. And the big surprise, at least initially 2 years ago, was that it looked like there were a bunch of galaxies only 500 million years after the birth of the universe, what we call the Big Bang, and they looked bright and big and mature. And this led to viral headlines like, "The Big Bang didn't happen." Well, the Big Bang did happen. The Big Bang theory, in its essence, has 3 components. The universe long ago started out hot, dense, and expanding. That's it. We're not telling you exactly what happened and why it happened at time equals 0, but a little bit after time equals 0, it was hot, dense, and expanding. That part is still true, okay? It's rock solid foundation. But there were a few people who said, oh, well, these galaxies look so old and mature, much, much more time had to have passed between the supposed beginning of the universe and the creation and evolution of these galaxies. And so that argues that the Big Bang didn't happen, or maybe was twice as far back in time as we thought. That's all a bunch of baloney, fake news, if you will. Put an X through it. Within a short time, science writers who knew something, this is just a month later, said no, James Webb Space Telescope images do not debunk the Big Bang. JWST provides an intriguing look at the early universe, but it's not yet rewriting fundamental theories of the cosmos. Now, 2 years later, by the way, we have learned enough from the Webb that certain aspects of the cosmos have been rewritten, but not a debunking of the Big Bang, okay? And these articles were written in response to the viral headlines. This guy, Ethan, he knows what he's talking about. He's got a good column, comes out every week or so. Look what he said, no. No, no, no. Just no. You can't be much more emphatic than that. JWST has truly blown our scientific minds, but it's a pure crackpot idea that the Big Bang is now disproven. I agree with that, okay? So what's going on? It's now 2 years later. We have some pretty good ideas of what's going on. One of the things going on is that stars form in bursts, in environments where the gas is particularly dense and star formation can occur rapidly. And for technical reasons, the stars that would have formed early in the universe were more massive than our sun, a lot more massive. And those stars are much more powerful, much more luminous than the sun. And so they contribute disproportionate amount of light. And if you assume that actually there were a bunch of stars that were lower mass and all that light is produced by low mass stars, then you incorrectly conclude that there's a zillion low mass stars there, and indeed the galaxy grew too quickly and matured too quickly. But the incorrect reasoning was to assume that there were lots and lots of sun-like stars instead of relatively few very massive stars that would form in this galaxy or that galaxy or that galaxy sporadically in bursts. And obviously the Webb would pick up this galaxy or that other galaxy that happened to be having a bright burst of star formation. But those were not representative galaxies back then. And moreover, the light we were seeing from them is not produced by large numbers of low mass stars like our sun, but relatively small numbers of much more luminous stars. The other thing that's going on is that we know today that galaxies have giant black holes in their centers, regions of space where matter is compressed so much that nothing, not even light, can escape. And so in an active galaxy, you've got a black hole, as in most normal galaxies, but there's material right near the black hole spiraling into the black hole. The black hole is eating the material. And as the material spirals in, it rubs against adjacent material. And it gives up its gravitational energy falling in, rubbing against its neighbors, that converts the energy into visible light and ultraviolet light and things like that. So these active galaxies, the most extreme versions of which are called quasars, apparently started forming in the first 500 million years. That itself is a puzzle. How do you get big black holes to form that quickly? Well, that's another puzzle, But some of those bright galaxies were bright not, again, because they have lots and lots of stars, 1 billion stars, but rather they're bright because a black hole formed quickly and there's stuff spiraling in, causing it to glow much more brightly than you would have expected. So those are the two dominant, I think, explanations at this point for why it looked like the Webb was finding lots and lots of very well-formed, mature, primeval galaxies. And the story is not yet done. There may be other partial explanations, and we don't yet understand how the big black holes formed, and we don't entirely understand the process of star formation in the early universe. But the Big Bang has not been debunked. Now, if we pass that light through a prism and produce a rainbow, a spectrum, you can measure these dark regions here, which are the signature of various chemical elements in the atmospheres of the stars or in the clouds of gas that are glowing in galaxies. And so you plot the brightness versus the color or wavelength of light from short wavelengths to long wavelengths. So here's plots of brightness versus color or wavelength. And this integrated circuit diagram shows you which galaxy you're looking at. But this one, familiar patterns of lines, in this case they're emission lines, excesses of light rather than deficits, but they're just sort of the opposite of each other. Don't worry about that. These patterns of lines are well understood, but they indicate that this galaxy is moving away from us so quickly that it has to be way far away in space and thus way far back in time. This one we're seeing as it was 11.3 billion years ago in a universe that's 13.8 billion years old. Here the same pattern of lines is shifted even further toward longer wavelengths, 12.6 billion years ago. This one, 13.0 billion years ago. Wow, that's getting pretty far back. This one here, 13.1 billion years ago. Only 700 million years after this Big Bang, the beginning, right? So we're getting there. Within 1 billion years of the birth of the universe, we can actually start studying the birth and evolution of galaxies that Hubble could not see. And one of the interesting aspects is that even in the galaxies that are existing in the universe when the universe was only 700 million years old, already there are significant amounts of heavy elements like oxygen and neon. And this is interesting because the Big Bang itself produced only hydrogen and helium and a smidgen of the next element, lithium. But already we're seeing oxygen and neon, reasonably heavy elements. That suggests that indeed there were already many bursts of the formation and final death of very massive stars in those first 700 million years, because it's that process of stellar birth and death that creates the heavy elements to begin with. So that's really quite interesting. Then there's an effect called gravitational lensing, where light from a distant galaxy, upon encountering a cluster of galaxies, gets bent. And so light that would initially have missed us actually reaches us. And that distorts and multiplies the number of images of background galaxies. They look like these arcs here. But just showing that again, without a cluster of galaxies, the light from a distant galaxy would have gone in a straight line toward us. But with the cluster, light that would have missed us gets bent toward us, and the background galaxies are stretched and made numerous images of through this gravitational lensing process. And this process indicates that there's not only visible matter, but also dark matter in the universe. And that's something that was already known, but the Webb has helped confirm it and allowed us to study it in greater detail. I'm part of a collaboration whose theoretical members said that these three little pinpoints of light are images of the same background galaxy, and it looks like it's a galaxy that's very, very far away when the universe was very young. So we passed the light from these objects through a prism and got a spectrum, brightness versus wavelength. And you see this pattern of lines that I showed you in the previous spectra. And it shifted so far to infrared wavelengths. Usually it would be at around 0.5 at this scale here. It shifted way over there, so that technically its redshift is this. Don't worry if you haven't been introduced to this terminology, but this amount of stretching corresponds to this galaxy being at a time that was only 500 million years after the Big Bang, so 13.3 billion years ago. And that was one of the record setters back then, not the only one. And now people have found galaxies that go back to when the universe was 400, even 350 million years old. I mean, there's papers that are being submitted for publication almost every week where astronomers are finding the yet most distant galaxy. But indeed, there's this gravitational lensing, and it is like a gigantic cosmic telescope because the gravitational lensing allows us to see much fainter and more distant galaxies than could be observed just with even a telescope like Webb without the gravitational lens. But the gravitational lens magnifies the light and makes it easier for us to see. So it's wonderful. Now, going to more nearby galaxies, this is known as Stephan's quintet. It's actually a quartet of galaxies, 290 million light years away, and one interloper along the line of sight, only 40 million light years away, so ignore it. But these are in a gravitational dance whereby they are attracting each other and gradually merging. And there are places here where lots of gas is colliding because these galaxies are coming together, and that causes bursts of star formation. And this is a prelude to what will happen or start happening in about 3 billion years when our nearest neighbor, the Andromeda Galaxy, only 2.5 million light years away, starts merging with our Milky Way. And you might say, well, wait, that's inconsistent with the expansion of the universe, right? Shouldn't it be moving away? It's sufficiently close to us that it's gravitationally bound to us. We're in the same cluster, so we're actually going toward each other. And the next cluster out is what's moving away. So these two galaxies will merge. They'll look like a train wreck for a while, and then they'll settle into a more or less normal-looking galaxy with a different shape than the spiral shapes of both Andromeda and the Milky Way. And astronomers already have a name for that final structure, Milkomeda or Milkdromeda, depending on your preference, okay? So Stephan's quintet and other galaxies in different stages of the merging process give us a prelude to what will happen to our galaxy. Numerical simulations of millions of stars, particles interacting with each other in computers can also tell us a lot about this process. Another reason to view the infrared is that you can see through clouds of gas and fine little particles, which we call dust, more easily in the infrared than in optical or ultraviolet wavelengths. And this is even more the case at radio wavelengths. On a foggy day, you might not see an office building a couple of blocks away, but you can still hear your favorite radio station. So long waves have an easier time going through gas and dust than short waves. So the infrared is pretty good about that. And there's this iconic picture, still iconic, from the Hubble, more than 3 decades ago, of what's called the Pillars of Creation, also the Eagle Nebula, or M16, in our galaxy. We've moved away from the distant galaxies now, only 6,500 light years away. And it had been widely thought that these are clouds of gas that are so dense and so full of dust that we just can't see through them. But some of that gas and dust is so dense that stars should have been forming in the past few million years and could still be forming now, and hence the name pillars of creation. And there were some radio data that support that hypothesis. But look at the infrared image produced by JWST. Now you can see all kinds of stars like this quartet that simply weren't visible in the optical image. Look at these ones there. They're not there. Well, they're there, but you can't see them. These ones there. Maybe that's one of them. I'm not sure. Whole bunch of them in here. Can't see them. These are stars that are newly formed, or in some cases still forming, in this stellar nursery. So the pillars of creation really was aptly named. And in the constellation Orion, his head, left shoulder, right shoulder, belt, sword, left foot, right foot. In the sword here, there's a well-known object known as the Orion Nebula. And it is a region where stars have formed in the past few million years and are still forming. And here you can see a Hubble optical image and the infrared image, whose visible light representation I'm showing here. Again, you should have that in mind in all these pictures. It shows lots and lots of stars that were simply not visible in the optical image. So that's kind of cool. And then if you take a close-up view of the bar, this part here of the Orion Nebula, you can see all kinds of interesting things. This boring, yucky star. But more to the point, look at this thing here. Here's a young star with a disk from which planets could be forming inside a cocoon of remaining gas and dust, which presumably, a good fraction of it got used up in the formation of the star. And then here's a young star still inside the globule of gas from which it formed, and there are all these filaments and stuff, all kinds of neat things here. So not just stellar birth, but we can look at stellar death as well. Here's the future of our sun. In 6 or 7 billion years, it'll become first a red giant, and then the outer atmosphere will only be loosely held by the sun, and it'll start drifting away, and there will be some instabilities within the sun that lead to gentle burps, cosmic burps, not massive explosions, but cosmic burps that gently eject the outer atmosphere of the sun, revealing the hotter inner layers, which then emit light that causes the surrounding gas to glow, to fluoresce. Well, in the Hubble images, it looked like that's the exploding, the dying star. This one wasn't visible. But the properties of that star, if you study them, do not agree with what a dying star should look like. So there was a bit of a puzzle. Well, at infrared wavelengths, you can see that there is this other star here. Its properties do agree with what we expect for a dying star. And the reason we didn't see it at optical wavelengths was that the ejected gases have already formed sufficient quantities of dust to block the visible and ultraviolet light from that star. But you can see it in the infrared. So there we go. We see this gently dying star. But in addition to the gently dying stars, there are the small minority that die in an explosive act of self-destruction. A cataclysmic event at the end of their lives where they literally blow up and become hundreds of millions or even billions of times as luminous, as powerful as the sun. And this field became activated by a great amount with the discovery of the closest such supernova to be easily visible in about 400 years. So now lots of astronomers study these things. And we suspect that dust particles are formed not just in regular, gently dying stars like this one, but also in explosively dying stars. So I'm part of a collaboration that's looking with the Webb at exploding stars whose light was visible 2 or 3 decades ago. And now we look at them with the Webb, and gosh, they're glowing a lot at infrared wavelengths. That's kind of cool. Means that there's a lot of dust there. And if you plot the spectrum, the brightness versus wavelength, you get all these dots. And the dots are reproduced best, in this particular case, if the dust consists of graphite, carbon, basically, like in pencil lead, as opposed to the other main way in which we think dust can form, which is in the form of silicates, sand. So you see the model with silicates has a dip here, which is not reproduced by the data, whereas the graphite model nicely fits these data points. So at least some supernovae produce carbon-rich dust, but others produce silicon-rich dust. Here's one that we published just this year, actually. You can see the Webb images of it at different wavelengths, and then here's the brightness versus wavelength. In this case, you do see the dip, at least a little bit, caused by silicon, and it doesn't fit exactly right because there are some processes that can lead to a contamination of these dots here, making them look a little bit too high. But I think you can convince yourself that certainly we're not seeing the upward trend at these wavelengths that you would have expected if there were a carbon-rich set of dust particles here dominating things. So some supernovae, exploding stars, produce graphite, and some produce sand, and others might produce some mixture or other things. Kind of an interesting way to use the Webb. Then, yet another reason to view the infrared is that you can see colder objects more easily. They emit mostly in the infrared. And then you'd go and you say, well, wait a minute, how about coals? Coals seem hot. Well, coals are hot compared to our usual terrestrial standards. You don't want to be touching them, or an orange hot stove. But stoves and coals are cool compared to most stars and most other astrophysical objects. But there are certain types of cool stars and things that can be thought of as sort of more massive than a massive planet, but less massive than a full-fledged star, that are cool enough to emit in the infrared, not mostly at visible wavelengths like our sun. So here I show three examples. A sun-like star. The sun actually produces white light, but it's usually depicted yellow. Its spectrum does peak in the yellow-green part of the rainbow, but there's blues and violets and oranges and reds, and physiologically we call that then white light. But anyway, its surface temperature, not that it has a solid surface, but the place where the gases become thick enough that they become opaque, that's what we call the surface. Roughly 6,000 degrees Kelvin, all right? A hotter star, 3 times as hot, emits some visible light, but more of its light at ultraviolet wavelengths. And a star that's half as hot emits some visible light, but more of its light is at infrared wavelengths. And some stars and some of these objects at the star-planet boundary become much colder than this, only 1,000 Kelvin, or even 500 Kelvin. And so their spectra peak way out here in the infrared, and there's very little optical emission at all. Indeed, the brown dwarfs, these objects at the star-planet boundary, until the mid-1990s were theoretically predicted but not yet discovered because there weren't very many infrared detectors around for astronomers to use back then. The military was developing infrared detectors because you can see glowing tanks at night. But astronomers are interested in the infrared as well, and actually there's some symbiosis there. We're both interested in infrared detectors. But initially these infrared detectors could only look at a small part of the sky and you couldn't do surveys, and so it was hard to find brown dwarfs. Now you can find lots of these objects that are too big to be called planets, but too small to be called stars, so we call them brown dwarfs. And there are now thousands of them known, and in regions like the Orion Nebula and the Eagle Nebula, the Webb is finding scads of them because they glow at infrared wavelengths. And recently there was one reported, a distant, very cold brown dwarf where At wavelengths that are almost visible, just a little bit to the infrared, there's nothing really visible there, maybe a bunch of noise. Then slightly into the infrared, you see a dot, a little bit more to the infrared. The dot is, well, perhaps even a little bit fainter, but then you get to even more infrared, longer wavelengths, and you can see the thing glowing a lot, okay? So this is a cold, distant brown dwarf. Kind of neat. All right, and then ending, or almost ending, very close to home, we can study even planets in our own solar system. And my colleague, Imke de Pater at Berkeley, studies Jupiter and Uranus and Neptune and all that. So here's the Webb picture of Jupiter with its great red spot, with which this color palette looks white, and the polar regions are a different temperature than the equatorial regions, so they look a bit different. But Imke had a quote which NASA probably didn't like very much. "We hadn't really expected it to be this good, to be honest," said planetary astronomer Imke de Pater, professor emerita at UC Berkeley, in a news release. Well, I was even worse. I said it wouldn't work at all. So I'm amazed they've given me any time after all the negative things I said, mostly not publicly. Now I say it in my public talks. I was wrong, and I'm glad I was wrong, okay? She just said we didn't think it would be quite this good. Anyway, so by studying planets like this, you can look at the development of storms on other planets and learn something about Earth's climate. Now, Earth is much more complicated, to be sure. It has oceans and continents and mountains and things like that, which complicate things a lot. Nevertheless, it is true that looking at other planets, we can learn about Earth's atmosphere as well. And here's Neptune with a ground-based picture. Neptune was seen overexposed when Voyager, a spacecraft, flew by in 1989 and showed the first images of rings, which we suspected based on other data were there. And that's the last time we saw the rings, because they're really faint, and ground-based telescopes don't do a good job seeing them. Well, guess what? There's the JWST image. By the way, that yucky thing there is Triton, Neptune's biggest moon. So let's get it out of the field of view. First, you see a whole bunch of other moons, and then you see the rings. Hey, look at that. There they are. And you see evolving storms once again. So it's useful to study planets in our solar system. And then finally, the infrared spectra of planets orbiting other stars, so-called exoplanets, can reveal the presence of water and possibly even biosignatures and technosignatures. So first, how do you find the suitable exoplanets? Well, if most stars have planets orbiting them, and we now know that that's a true statement, but they have randomly oriented orbital planes, most are not good for this type of study. But those that happen to be edge-on to our line of sight, well, gee, in those cases, once per orbital period, the planet will pass between the star and us, and the opaque part of the planet will block some of the light. So if you monitor the brightness of a star as a function of time, and when it's out here, the brightness of the star is constant when the planet is out here. But when the planet starts blocking part of the starlight dips. And this is a bit of a misleading plot. You might not see the labels here, but this is like 0.98, 0.99, 1.00. In other words, 0 is way down in the sub-basement of this building. The light drops only by a little bit, 1% at most. For an Earth-like planet, 1/100th of a percent. Nevertheless, that can be noticed. And if you then look at the Webb, use the Webb, to get a spectrum of the star during a transit, like this, and not during a transit, and you compare the spectra, they might look a bit different because that light from the star travels through a transparent atmosphere that might be there. And although the atmosphere is transparent at most wavelengths, it will selectively absorb certain wavelengths depending on the atomic and molecular composition of the star, of the atmosphere, I meant to say. So this is a well-known technique. You pass the light, again, through a prism, measure the relative brightness of these different lines during a transit and not during a transit. And if a certain element is present in the atmosphere, but other elements are not, then absorption lines from that certain element will look, relatively speaking, stronger. And this has been shown many times, even with the Hubble Space Telescope. Sodium was found in the planet orbiting this star, whose name is that. So that's, all right. So this has been done already many times with the Webb, but I'm showing the very first case that they highlighted, just because it was part of their initial press conference. A spectrum, brightness versus wavelength, and there are all these noisy data points. It's a hard measurement to make. But the blue curve is a curve that's based on a model that includes water. And the bumps and wiggles, the bumps and dips follow what you expect if there's water in this atmosphere, which is really interesting because this is a planet that orbits the star once every 3 days. It's really close to the star. We orbit once a year. Mercury in our solar system orbits once every 88 days. So this planet is really close to the star. You might think all the water has evaporated away, but no, some of it is still there. And so this suggests that water could be present in a very wide variety of environments of exoplanets. Close to the star they orbit, far from the star, in gaseous form, in liquid form, in solid form, with maybe puddles underneath. And astrobiologists, those biologists who want to study extraterrestrial life, they have a mantra: follow the water, in that all of life on Earth that we know of, at least right now, is based on water and carbon, by the way. Sooner than we might hope, it could well be taken over by silicon-based life, right? Not to scare the youngsters here, but our evolutionary descendants may well be computer chips, robots. But at least in terms of life forming in a natural way from the elements that are just scattered around on the surface of a planet, almost certainly, most of the time, it begins with water and carbon, although I don't disagree that there could be other ways. And so if water is found in the atmosphere of an exoplanet, other astronomers will use their telescopes to start looking at that exoplanet to find signatures, not just of water, but of life. And there's the possibility that someday the data might become good enough that not only will we detect water, which we've already done, but this is a synthetic spectrum, a fake spectrum of what we might hope to get. But methane, CH4, in the presence of oxygen, ozone in this case, that would be interesting because methane oxidizes very, very quickly, turns into other things in the presence of oxygen. So if you see simultaneously methane and oxygen, it means there's some sort of a reasonably continuous source of methane. That could be purely chemical, of not biological origin. And indeed, on Mars, there are varying amounts of methane, not so much oxygen, but we see varying amounts of methane. And most astronomers think that there is no clear evidence for life on Mars based on that methane. It's just a chemical reaction of a biological origin. But it could be of biological origin. Carl Sagan used to call it bovine flatulence in his eloquent way of speaking. So this would certainly be a signpost for possible life. And if we could see signs of technosignatures, for example, pollutants, chlorofluorocarbons, which fortunately we don't use very much anymore in refrigerants, or at least we don't let them escape haphazardly because they destroy our ozone layer, which protects us from the ultraviolet light from the sun. But anyway, if we saw pollutants that we didn't expect to see in the atmosphere in some natural way, that would be really cool. I think the odds for that with the Webb are low, but it's not impossible. So I hope I've given you a flavor of what sorts of things the Webb has been doing, and we anticipate that it'll be working for 20 or so years, unless it gets hit by a rock, a meteoroid. Initially, it was thought to maybe last only 5 years, and it would run out of fuel with which we could shepherd it back to the L2 point. But the engineers planned the whole launch so well that on its way to L2, it had to be nudged only a little bit to get it there instead of nudged a bunch of times. So imagine you're here in Delaware and you're playing golf and you want to hit a hole-in-one in San Francisco. And in a normal golf game, you know, you'd be helped out in Wichita and in Reno and in various places. But instead, you got helped out in Berkeley a little bit, and it nudged you to San Francisco. It was almost a hole-in-one. So they didn't use up much of the fuel. And that means there's more fuel left over to nudge it into place, hopefully for 20 plus years. And I'm certainly thrilled that it has worked so well. And I was told to speak for about an hour, and I'm 4 minutes over. But let me end with the fact that astronomical research of this sort relies, of course, on support, financial support from government agencies like NASA and the National Science Foundation, but progressively more on foundations and companies and private individuals and families. And so again, I'd like to thank the Mount Cuba Foundation, which I didn't specifically list here, but I know that they've helped out with the Keck telescopes, which I use quite a lot. But thank you, and I hope there's some time for questions before you all go running off to see what the debate is all about. But of course, it'll be replayed over and over again online, so there's no huge reason to see it live. And I'll be happy to answer questions as long as you'd like. Thank you very much. And I'll repeat the questions for everyone. Yes?
Earlier you mentioned that there were a lot of papers coming online about new...
Yeah, lots of papers coming along about new discoveries.
Right, just a couple of 100 million years after.
Yeah.
Was that based on the research from the JWST? Or was it also Keck and Hubble?
Yeah, so the question is, you know, what is the source of all these papers that are talking about these young galaxies and stuff? It was mostly based on JWST because it's the only telescope that can detect these things in the infrared. You know, Keck is a ground-based telescope. It has available to it what's called the near-infrared, the part of the infrared that's able to make it through Earth's atmosphere, and a wavelength at which Earth's atmosphere itself doesn't glow all that brightly. But most of the infrared is not accessible from the ground. And so it's been the Webb. It's been just a dynamo at this sort of stuff. It's amazing at how productive it has been. Yeah, good. Yes, right over there.
Yeah, the further you go back in time, further you look back in time with JWST, the more you're looking at visible instead of infrared, right?
So the statement is the further back you look away, the farther back you look away, the further back in time you're looking. And so the light becomes more and more infrared, not more and more visible.
Well, it's coming back. It doesn't start as visible and become infrared.
Yeah, it started as visible or ultraviolet, but then on its way, space stretched, and that stretched the wavelengths as well. So it becomes infrared by the time it reaches us. That's why the Webb is so unique compared to, say, Hubble at looking at the very first galaxies, because they're so far away that, oh, and you could say, well, what about X-rays that were emitted by those stars? Wouldn't they be shifted to the visible, and so maybe then Hubble could see them? Good thing, if you were thinking that, good idea, but stars don't intrinsically produce many X-rays. They produce, depending on how hot they are, ultraviolet, visible, and infrared. So the best you can do is ultraviolet. And for the hottest stars, those are pretty short ultraviolet wavelengths. But if you go far enough away and thus back in time, even those reasonably short ultraviolet wavelengths will have been shifted to the infrared. So you have no choice but to look at the infrared. Does that make sense?
Yes, but my point really was that when you look that far back in time, now you're looking at visible and UV instead of infrared. And for the dust area far back, with that, now you're not getting the infrared goes to the dust.
Yeah. So the point that's being made is that how are we seeing the infrared that was emitted by those stars and which went through dust? Right. Well, one of the nice things about the Webb is that its span of infrared wavelengths is very large. There's what's called the near infrared, the mid infrared, and the far infrared. And so the near infrared maybe gets shifted to mid or far infrared, but we can still see it. But indeed, dust is still one of the problems, but we can see at least some of the light that went through the dust. Moreover, along these lines, something I didn't have a chance to mention, but it's actually relevant, one of the reasons astronomers thought that some of these newly formed galaxies looked so big and bright and mature with a billion stars is that they said, well, the Webb is able to look at intrinsically infrared wavelengths. They just got shifted to the longer infrared. And so we're seeing the relatively normal stars. And to have such a bright galaxy made out of relatively normal stars, you needed really a lot of normal stars. So that was one of the points of using the Webb, was that the Webb will allow us to see the relatively normal stars. And if galaxies are bright and big, then that'll mean that they formed quickly. And that was just too rushed a conclusion. Yes, they're bright, but they're bright because of relatively few, very massive, very luminous stars, or gas swirling around a central supermassive black hole. It's not the case, despite what we wanted, that we're seeing the light from a gazillion low-mass, relatively normal stars. But we could have, and I just thought that was a bit too much into the weeds to discuss, but in answer to your question, it's a very good point. Yeah, yes, right here.
Is there a chance we'll be able to see population 3 stars?
So the question is there a chance we'll be able to see population 3 stars? Oh my goodness, there's some good jargon. You know some astronomy. All right, so the population 3 stars, kind of not intuitively, was the first set of stars to form, not the third set of stars to form. That's the idea, to try to find, if not single population 3 stars, then clusters of them. And indeed, some of these starbursts we're seeing may well be among the first generations of stars. So far, we've not found any whose spectra have been taken that show only hydrogen and helium, and maybe a little bit of lithium, which is hard to detect. They always show some oxygen and other stuff too, which means we're not seeing the very first generation. But it doesn't take much time for massive stars to have contaminated or seeded the space around them with gas that's been enriched in heavy elements, because the most massive stars only live a few million, let's say 10 million years in their normal lives before they blow up. And then you can form new ones reasonably soon thereafter, not from the ejected material of a single star, but the ejected material from various stars coalesces and then you can form a new star. But in 100 million years, you could actually have several generations of very massive stars. And we have not yet seen definitively the first generation. But depending on what you define as population 1, 2, and 3, there are no hard boundaries. We're getting damn close, okay? Yeah. Yes?
What do you think of the feasibility of white holes?
What do I think of the feasibility of white holes? So if you look at the mathematics of black holes, then for what's called an idealized black hole, not one that formed from a real collapsing star or a real collapsing cloud of gas, but one which existed with the birth of the universe itself. It was part of the curvature of space-time, so to speak. A black hole connects through an Einstein-Rosen bridge, colloquially called a wormhole, to the other end, which, would be a white hole if we could view it in our own universe. It's a region out of which stuff comes, but into which nothing can go. Now, we've never seen such an object in our observable universe. They would be super easy to find. I mean, black holes are hard to find because they don't shine, okay? But white holes, they should be easy. And in the mid-1960s, people briefly considered white holes as a possible explanation for the very luminous objects called quasars before it was realized that they're actually big black holes with a bunch of stuff, swirling in. So we don't have any definitive examples of white holes in our universe, and that probably means they don't exist. And it's reasonably easy to see why they probably don't exist, and that is that as soon as you try throwing something into a black hole, even an idealized one, and it can't help but swallow some stars or surrounding gas or whatever, the material going in achieves such a high energy density, so much matter and energy per unit volume, that it squeezes the wormhole shut. So in fact, nothing can get through. Or it's also possible that this mathematical idealized solution is mathematically valid, but is not something that is realized ever in nature. And there are other cases like this, where sometimes a mathematical solution is something that physicists look for and then they find it, and other times they don't. Let me give you two examples. There's the Schrödinger equation in quantum mechanics, which describes tiny little things. And usually you deal with small speeds and stuff. But then there's the relativistic Schrödinger equation, which is called the Dirac equation, Paul Dirac. And he showed that, theoretically, out pops something that looks like a positively charged electron, or a negatively charged proton or whatever. So he said, well, experimentalists start looking for these things, and lo and behold, positrons, positively charged electrons, were found, as predicted. But in other cases, the mathematical solution has never been found in nature. And an example is that in special relativity, you have typical particles always travel slower than the speed of light. And it takes an infinite amount of energy to accelerate them up to the speed of light, which is why it never happens to any particle that has non-zero mass. Light, by the way, travels at the speed of light because it has no rest mass. But anyway, it takes an infinite amount of energy to accelerate a particle up to the speed of light. An equally valid mathematical solution to Einstein's special relativity equations is that there are objects called tachyons that always travel more quickly than the speed of light, and it takes an infinite amount of energy to slow them down to the speed of light. So there are physicists who have spent their entire careers looking for these things. I'm a short-term opportunist. I could not do that kind of research. First of all, what do you look for? How do you even know how it will interact, right? You look for flashes of light, or So they've never been found. Maybe someday they will be found, or maybe nature doesn't produce them. And a very simple example is that in certain physics lab experiments, students are asked to find the mass of an object, some pendulum or something, some bob. And what they end up getting is the square of the mass. And so let's say in some experiment, they find that this hanging weight or something has a square of the mass is 100 square grams. So then we ask you, what is the mass of the object? If the square of the mass was 100 square grams, you tell me, what's the mass? 10 grams. But what's an equally good mathematical solution? Negative 10 grams, right. We throw it out as being unphysical, quote unquote, because no one has ever found anything with negative mass. The dark energy has something called a negative pressure, not a negative mass. But who's to say some whippersnapper someday won't find an object with negative mass and win a Nobel Prize and stuff? It could happen. I doubt it, but maybe it will happen someday. But there's a case we don't know in some of these cases whether the mathematical solution is necessarily something that nature chooses to adopt. And it's a bit of an argument that becomes almost philosophical. Indeed, partly philosophical, partly experimental. We can say no tachyons have ever been found, no negative mass has ever been found, but then you can philosophize and say, well, we just haven't looked hard enough. Some physicists adamantly believe that if your theory is beautiful and complete and all that, any mathematically valid solution will be something that nature chooses to adopt. I'm not so sure, okay? So the white holes and all that, That was a bit of a long answer. Sorry about that, but it's an interesting question. They're all interesting. Okay, over there now. Mhm.
Could the Webb be used to track asteroids or comets that might be
Oh yeah, so could the Webb be used to track asteroids or comets that might be headed toward us? In principle, yes. Not so much as a search engine, because the Webb looks at small fractions of the sky, okay? There's going to be a telescope very soon. It's being built in Chile, called the Vera-Rubin telescope. Arguably one of the few discoverers of dark matter was Vera-Rubin. And it'll take pictures of giant old huge parts of the sky, and so then you can compare one picture with another and find objects that are moving. You could then point the Webb at the object that you have found with a wide-angle survey. It's not all that great a use of the Webb, because there are other telescopes that you can use, like the Rubin, to track that thing's trajectory among a bunch of stars in the sky, and that's useful, because then you can track the trajectory more accurately when you have lots of comparison stars and stuff, and then you can figure out whether it's going to be something that has the potential to hit Earth. And if it does, and you figure that out 50 years ahead of time, then clever applied physicists and engineers can figure out a way to deflect it, as was done, in a sense, in a proof of concept experiment, the DART mission about a year, 2 years ago, something like that, right? Where they blasted a satellite into the moon of an asteroid, and they clearly changed its orbital period by about half an hour out of something like 5 or 6 hours. And so that was a proof of concept that we can deflect these things. So certain telescopes have strengths and weaknesses, and tracking asteroids is just not what I would call one of the Webb's strengths. There was a question in the back there. Yes, go ahead.
So this is looking at, electromagnetic radiation.
Yeah, electromagnetic radiation.
Is there any thoughts about marrying that with like Ice Cube looking at, neutrinos, down
Yeah.
in the early universe?
Right.
There was a paper that was written, which I don't understand, but I picked out, magnetic monopoles.
Yeah. Right. So, there are various other techniques that astronomers use. Most of them get electromagnetic radiation, but there are certain techniques of looking at other clues about the universe. The most obvious is, the moon rocks brought back from the moon, or meteorites that land here and stuff like that. So there's these particles called neutrinos, and they're very interesting. They're extraordinarily low mass. They were thought for a while to be massless, but they've got a little bit of mass. And they were produced by the early universe. There's something like 400 of them per cubic centimeter, something like that everywhere. But they go through your body. They don't do anything. They don't cause cancer or anything like that. Ice Cube is an experiment down at the South Pole where, when the neutrino travels through enough dense, clear ice, it can actually interact with the ice occasionally, very, very rarely, because neutrinos mostly don't interact. And that can produce a flash of light or some particle or something like that. But the neutrinos that are most likely to interact are very high energy neutrinos created by two dense stars, like neutron stars hitting each other, or the explosion of a star, or something like that. The ones from the early universe are very low energy at this point, and it'd be hard to tell whether any neutrino you detected was or was not from the early universe, right? They don't have labels on them. But now what astronomers using Ice Cube have done is they've said, oh, there's some other explosive object over there. Certain galaxies with giant black holes sometimes go through flares and stuff, and there's all these high energy photons and other stuff. And lo and behold, a neutrino was found coming from about the right direction. So that's more of what Ice Cube has been finding so far. Will it someday be possible to find neutrinos from shortly after the Big Bang? Maybe, but it's going to be a tough job. On the other hand, I said that gravitational waves wouldn't be detected anytime soon, and I was wrong. They were detected in 2015. I'm wrong a lot of the time, basically. It keeps the science more exciting. Perhaps I'm too wedded in my old ways. I'm too conservative in that sense. And but I also, I think, try not to have greater expectations for certain types of telescopes and thinking that they're going to be solving all the mysteries of the universe, because let's face it, very few of the telescopes have solved all the mysteries of the universe. 0 by my count so far. So having that conservative view is not a bad thing. Yes?
So one of the things that I'm really excited for Webb about is the techno-signatures.
Yeah, the techno-signatures would be exciting.
Exoplanets.
Yep.
Regarding their signatures, I mean, what kind of, even with more advanced software, do you maybe in the next 10 years, do you think Webb is going to really be able to get down to the nitty-gritty of transiting maybe
Yeah.
planet or maybe even an exo-moon in the future?
Yeah.
And it can really just show like there's like non-normal elements
Right.
in that atmosphere, and also how can we more accurately determine whether it's truly from that planet or it could be
Yeah. So the question is basically how likely do I think Webb is to find definitive evidence of a techno-signature, something that is not naturally expected in the atmosphere of a star. And of course, you know, my brother and I used to have these arguments. He would say, well, people are part of nature, and so things we create are natural. Yes, I agree with you, dear brother, but that's not the sense in which the word natural is being used, okay? Right? Natural, not made by intelligence of any sort. So chlorofluorocarbons, you know, they exist in nature, but they're extraordinarily rare, and people make them, you know, as refrigerants and stuff. And so if you find a huge concentration of chlorofluorocarbons, not that it's most of the atmosphere, but a huge concentration compared with what you would expect just based on, you know, chemical random reactions and stuff, that would be pretty amazing. But nevertheless, the signature of that pollutant is likely to be extraordinarily faint, a tiny little dip, right? Because in our case, our atmosphere is 79% nitrogen, 20% oxygen, good fraction of the remaining 1% is argon, there's some CO2, there's H2O, carbon dioxide, water, et cetera, et cetera. So these are, and any, you know, anything we produce, even though we have been polluting the world, you know, compared to the overall spectrum of our atmosphere, it's likely to be a very faint, hard to detect signal. And the amount depends on how much of a concentration there is and whether the various levels of the molecule are easily excited, blah, blah, blah. But I expect them to be very faint little signals, you know, fainter than that little thing there. And so you need an extremely low noise spectrum, right? This synthetic spectrum has no noise in it. There's no just jittering around. I mean, you see some jittering around. You see a lot of noise here, right? See how much the data points jitter around? Imagine some little tiny dip there. You'd never see it in the data. And so you have to expose a heck of a long time with JWST to get a sufficiently good spectrum with extraordinarily low odds of success. And meanwhile, there are all your colleagues who want to use this precious resource for their own projects. It's hard to get time. The oversubscription in a given year is about 8 or 10 to 1, meaning, let's just call it 10 to 1. There are 10 times as many proposals in a given year as can be accommodated in that year of observing time. So it's very competitive. You have to justify what it is you're going to do. It's got to be reasonably realistic in terms of a detection. And saying you're going to find some weirdo compound that some alien Romulan thingy produced it's not going to fly, probably. So I'm reasonably pessimistic about this aspect of the Webb. But in 5 or 10 years, when they find one of these things, you'll say, Alex Filippenko was wrong. And I will be overjoyed, because even though I personally don't, study exoplanets, I have one student who did a little project, and I certainly have not sunk my teeth at all into looking for extraterrestrial life. I would be delighted if it were found. It would be one of the greatest discoveries in the history of humankind. Yeah, absolutely. Yes, right over there. And then over there.
A little off topic, but more Filippenko. So
Okay. By the way, thank you all for coming. The debate started 10 minutes ago, but I'll go on as long as you'd like me to. Go ahead.
Do you have any comments about the research out of Hopkins and out of the University of Chicago regarding the Hubble tension?
Yeah, the Hubble tension. Oh, I have a lot to say about that. I'm intimately involved with the Hubble tension. And by the way, those of you who need to leave, feel free to do so. Graceful exit, whatever. So the Hubble tension that's being mentioned is the following. Very briefly, you can measure the current rate at which the universe is expanding. And here I actually even brought an expanding one-dimensional universe, okay? Boom. The galaxies, the ping pong balls, are gravitationally bound. They're not expanding. But the current expansion rate is some number of kilometers per second, so it's a speed per unit of distance. And the reason there's a unit of distance is because obviously the farther a given galaxy was from you to begin with, the more space there was to stretch, and hence the greater was the speed, if I just expand this thing for 1 second. So in some units, we find that the current expansion rate is 73 kilometers per second per million parsecs, which is like 3¼ million light years. But there's another way of doing it, and that is that you take the measurements that our radio astronomer friends do, in particular microwave measurements, of the early universe when it was only 380,000 years old. It's called the cosmic microwave background radiation. And they see all these little spots, these little freckles. You maybe have seen them before. And without getting too much into the weeds, from those freckles and the standard model of cosmology, which says that 70% of the universe is dark energy of the kind that is a property of space itself, rather than some kind of energy flying through space, like light, but not like light, but there's a subtle difference there, a property of space versus a new type of energy in space. But anyway, 70% of the universe is this repulsive property of space. 30% is attractive stuff, mostly dark matter. And you propagate that forward, and they predict then a current Hubble constant or Hubble parameter, that is expansion of, and they get 68.4 plus or minus 0.6, and we get 73.0 plus or minus 0.94, I think is our best measurement. And those now differ at the level of 5 standard deviations, 5 sigma for those who have done statistics. There's only a chance in a couple of million that nature produced such a statistical fluctuation by chance, and it's not telling us something interesting about the universe. So that's the tension. So the obvious solutions are, well, we've done something wrong with our current measurement, but that seems unlikely because there are other techniques and other groups that get basically the same measurement, except for Wendy Friedman at the University of Chicago. But I respectfully disagree with her, and she finally came out with a paper after, I shouldn't be critical, but we've heard about her result in conferences for 3 years, and reporters are reporting on it, but there's not been a submitted research paper that other scientists could analyze. Now, her group has one, and we, within 2 weeks, came out with a rebuttal paper, which we also posted on the archive, showing where we think our differences are in the analysis. But most groups agree with us, 73. She gets 70. And I have no huge reason to not trust my colleagues who deal with the microwave background. There's a number of groups who have analyzed the data. So I think they're correct in how they analyzed it. So I think there's something wrong with the standard model that's being used to predict the current expansion rate based on the early universe observations. And that would be very interesting. Like maybe the early universe had a boost. The example I give, it's not exactly correct, but you're watching a kid's soccer game and you're kind of myopic, you're looking in one direction, and you see a soccer ball zipping by faster than any one kid could have kicked it. Well, what if another kid kicked it first in the same direction, right? Your model was wrong, your assumption was wrong. It's not anything that you did wrong that you made a big boo-boo, your assumption was wrong because you couldn't have known about the other kid. Maybe studying teams, you could have thought that that's a possibility and stuff, but it's not something wrong like a programming error, 2 + 2 = 5, or measuring the brightnesses of stars in an image incorrectly or something silly like that, right? So I think there's something wrong in the standard model. It's incomplete. Very, very interesting, if true. And I think the Hubble tension is a real thing. I don't know, Federica, my colleague, do you think it's real, the Hubble tension?
I do think it's real, and dark energy doesn't have to be a constant.
Yeah, dark energy might not be constant. That's the other thing, is that it's not a property of space itself. Rather, it's a type of energy whose energy density, the amount per unit volume, can change with time. That's a possible explanation. Yeah, how about right over there? Yes.
So before you mentioned the theoretical existence of negative gravity,
Yeah, negative gravity theoretically.
I'm curious what you think, how you think time dilation would apply to that.
How do I think time dilation would apply? Well, that's an interesting one. So what the gentleman is talking about is that when you go deeper and deeper into a strong gravitational field, your clocks, as viewed by people in a less deep, weaker gravitational field, slow down. And it's a purely general relativistic effect. You might say, that sounds weird. It is weird. But there is something we rely on every day where the physicists and engineers who designed it utilized this fact. They had to take it into account. What is it? GPS, that's right. The satellites up there have clocks that are running more quickly than the clocks down here. So I've never considered the equations with negative gravity. So I'm speaking completely off the top of my head here, but maybe it goes the other way around. Maybe time speeds up in a relative way. But it's important to note that as measured by you on your own clock, time is always going at the same rate. It's always people looking at you, and it's a relative measurement. But yeah, might be interesting to explore mathematically. I've never done it. You can ask ChatGPT and see what it thinks. Yeah. Oh, right there. Yes, go ahead. Sorry, I was being myopic here.
So in terms of galactic mergers, could you comment on anything that we're seeing or learning new with galaxies in the early universe with Webb?
Yeah, galactic mergers. By the way, if I don't end up getting to your question, here's my email address. What can we learn about galactic mergers with Webb? So I showed you Stefan's quartet, and that they're in a certain stage, maybe 1 billion years from crashing totally into one another. But then they kind of go through each other. Most of the stars, almost all the stars, never collide, but they gravitationally interact. And then it kind of looks like a train wreck, and it's all moving around, and then it kind of settles into a more or less elliptical galaxy, as we call it. We learned that by looking at numerical simulations. So computers are now able to deal with tens, even hundreds of millions of particles, stars, even billions now, right, because of Moore's law. And we can compare that with different stages of the merging process that different pairs and triplets and quadruplets of galaxies are in. Obviously, we're not going to be around watching this for 1 billion years. That would be not a very smart PhD thesis topic to choose, okay? But what you could do is take pictures of galaxies in different stages of merging. And so I showed you Stefan's quartet. Going back to the early universe, it's quite clear now that despite some of the bright, seemingly well-formed galaxies that JWST found, there's a bunch of little bits and pieces of what we would call galaxies. And for sure, over the course of time, many of those merged together to form bigger galaxies. And so I'm not that involved in the work that has been done, but just recently, I think JWST zoomed in on this apparent question mark in space, right? Did you see some of those headlines? There's some weird grouping of galaxies that looks like a question mark, like that's where the key to all our answers is. No, it's just 3 or 4 galaxies that are in the process of merging, and they happen to look like a question mark and stuff. But Webb has only been around up there for about 2 years of taking data so far, and we hope it's there for 20 years. And so with time, more data on the merging process will surely be obtained. So far, I think they've just seen a few cases where it's in different stages of merging, and I showed you one of them, but we don't yet have the means to follow lots and lots of examples of this sort just because there hasn't been enough time to look at enough such objects yet. Yes, right there.
I was wanting to know about when you're talking about transients,
Yeah.
you're talking about how looking at photometry, you can determine if they are predominantly silicate or
Oh, the supernova, not the transits. Right, yeah.
how are you able to tell that from photometry alone?
Well, how do we tell from photometry alone? Photometry is a way of measuring the brightness of an object at a particular range of wavelengths. So this point here might correspond to 12 plus or minus 0.5 micrometers, all right? And that point there might be 11 plus or minus 0.5, and this one is in the range 10 plus or minus 0.5. So photometry over a bunch of different bands is a form of what would be called low-resolution spectroscopy, right? This is a poor person's spectrum. Right, it's not just that we took the overall brightness at all wavelengths summed together. No, this is brightness versus wavelength. So this is a spectrum, but it's a very crude spectrum. But even with this crude spectrum, you can see that graphite should produce a bump here. I mean, well, silicate produces a bump there as well. But the point is, it's on the upward trend here going to longer wavelengths, whereas silicates produce a dip. So this very crude spectrum argues more for the presence of graphite than silicates. Yeah, does that make sense? Yeah, good. Okay. Yes?
So as you said, James Webb was not the successor, but the complement.
There you go. Complementary to Hubble.
Right.
Thank you. I've got like $20 for you afterwards.
So 30 years from now, what do you think the complement to James Webb will be?
Yeah, what do I think the complement to James Webb will be? So in some ways, we're in a golden age of spacecraft, and in other ways, it doesn't look so rosy. There are a bunch of spacecraft up there. There's a European thing called Euclid that's studying the distribution of galaxies, and there's going to be a thing called the Nancy Grace Roman telescope later this decade, only a few years from now, that'll study wide swaths of the sky and will look for things that go bump in the night and also weak forms of gravitational lensing and things like that. We've got on the ground the Vera Rubin telescope. We've got maybe a 30-meter telescope, one or more from the US, although the funding looks uncertain. But the Europeans are definitely building a 39-meter telescope in Chile. So that's all really great. And then there's a thing being planned for maybe 30 years from now called the Habitable Worlds Observatory. Again, I'm not much of an exoplanet person, but is that about right? 30 years from now, Habitable Worlds Observatory. So that all looks good, but having said that, these projects are getting really expensive. The Webb was $10 billion, and unless you find some technical way to greatly reduce the costs while building a bigger general purpose telescope, like going from 6 meters to 60 meters or even 25 meters in space, you know, an order of magnitude more collecting area, you know, it's really expensive. And you saw what happened to the superconducting super collider in the US. You initially lowball the price, otherwise Congress doesn't even approve you, and then the price creeps up, and that's understandable. But then it creeps up so much that you get canceled. And the superconducting super collider in Texas got canceled when the price tag reached, I think, $23 billion and no end in sight. So there's the Large Hadron Collider at the border of France and Switzerland. The US is involved, along with 79 or so other countries, but we are not the leaders of the Large Hadron Collider. We ceded that to Europe, basically. So how much money is society willing to spend when there are many issues, including, right, my generation being responsible for youngsters in the future not having Social Security or Medicare or something unless something dramatically changes, right? I mean, you just do the math. The baby boomers, right? And I'm sorry about that. Many of you, you're baby boomers as well, you know. So But yeah, there are a lot of societal needs, and we're very grateful to what society gives us, but this is why, we're relying more and more on people in foundations and companies and stuff like that, right? It's like a hamburger per person to have made the Webb, let's say. Well, maybe a bit more than that. The Webb cost $10 billion. And let's say there are 200 million paying adults. So 1 times 10 to the 10 divided by 2 times 10 to the 8. So that's 10 times 10 to the 9 divided by 2 times 10 to the 8. 10 divided by 2 is 5 times 10 to the 1. $50, unless I messed up somehow, is what each of you taxpayers paid to make the Webb a reality over many, many, many years. So it's like 1 hamburger per year. It's not a lot. But a lot of people, present company excluded, say, why in the world should we give you guys and gals, I'm saying guys collectively, anything when you're just sitting around in your ivory towers doing this research that's never going to benefit anyone? So that's one reason I feel it's important to give public talks, to give back and to show why it's important. And my elevator speech, depending on whether I meant, how much time I have, if it's a member of Congress, I have about 27 seconds in the elevator. It's other venues, it's something else. But, I can think of at least 3 reasons to do this kind of research. First, humans are the only kinds of animals that have the cognitive ability and the inquisitiveness to ask questions like this and answer them, and with their opposable thumbs, build machines with which to answer them, and so on and so forth. And so it's one way we set ourselves apart from all other animals. Secondly, the results of this kind of research are exciting to children. I remember the lunar landings. I was 11 in 1969, and I was already dedicated, I thought, to a life of science, but I didn't need any more inspiration, but I was still inspired. But I had friends who said, whoa, this is so cool. People have landed on the moon. Let's go into STEM fields. So they were more likely to go into STEM fields after being bitten by the bug of astronomy and high energy particle physics and things like that. And most of them go on into fields that are more immediately useful to society. Applied physics, medical physics, computer science, engineering. But the bug that bites them is this kind of stuff, right? A few become professors of astrophysics. You don't need many of us in the world at any given time. And then finally, there are the unanticipated spin-offs. And to give you an example, my favorite, a century ago, physicists were interested in 2 main problems: the nature of light and the stability of atoms. Atoms should be unstable, and light, who the hell knows what it is? Well, you could say, well, why do you care? As long as Thomas Edison could make a light bulb by passing currents through wires and stuff, and we have better and better light bulbs, what do you care what light is? And as long as atoms are stable, what do you care about why they're stable? Well, the physicists cared. That then ushered in the birth of quantum mechanics, quantum physics. Fast forward 100 years, you could not imagine life today without an understanding of physics on nanoscales. In particular, there's 500 million transistors on the head of a pin inside this thing, right? And lasers, a purely quantum process, et cetera, et cetera. And then in the context of gravity and general relativity, Einstein had not the slightest practical application in mind when he was thinking about the nature of gravity. Fast forward 50 years and you get GPS with all of its initially military and now commercial applications. So you never know what might happen. So there's my elevator pitch.
That was a lot more than 27 seconds.
Yeah, I know. That's because you're not members of Congress. But anyway, it isn't unreasonable for reasonable people to ask why this kind of work should be supported through taxpayer dollars at all. So I'm grateful for the career I've had and from funding from the National Science Foundation and NASA. But National Science Foundation and NASA, they're part of the increasingly infinitesimal, so I'm taking 2 reciprocals there, but slice of the federal budget, of the discretionary spending that's spent on this kind of research. NASA budgets are being slashed this year. I mean, I have Hubble and Webb proposals where they've told me, you submitted a budget that was approved last year, and guess what? You now have to cut it in half. Yeah, or a third. And this year's Hubble proposals, even though they were accepted way back in June, I still haven't been requested by NASA to submit an associated budget. In previous years, within a week, they would say, send in, within another month, your budget request for graduate students and hungry mouths to feed that will help analyze these data. They really should be analyzed and published because, hell, we spent billions of dollars putting the Hubble in space, well, loosely speaking, and if nothing ever gets published, then that was sort of a waste of money, right? So in the end, the publications and the discoveries are what counts. But you need graduate students and postdocs and undergrads and hungry mouths to feed and stuff like that. And it's becoming harder and harder, right? Yeah, so, yeah. Question back there. Okay. Sorry, could you speak up a bit louder? The immediate conversation. Okay. Yeah. Right. Yeah, can we make something smaller and lower budget? That's exactly the kind of technological thing I was referring to, that we need better new ideas. And indeed, there's one idea of, specifically for exoplanets, where you stick a thing out there and it almost looks like a flower. It's got all these petals. It's much smaller, I think, than these giant James Webb things. But it effectively shields us from the light of the star. Or specific purpose missions can be much less expensive than a general purpose machine like the Hubble or the Webb, which is supposed to please everyone all the time. The Kepler mission for exoplanets was a great example. It was 600 million or something like that. And it discovered thousands of exoplanets. It was fantastic at doing that one thing. And by the way, clever astronomers then said, well, it didn't just do that one thing. It monitored the brightness of stars, and you can do something called astroseismology. And I know there's an astroseismology group here at University of Delaware. But if you plan a mission that's focused, right, you can often do it cheaper. And indeed, Euclid and some of these other things are going to be more focused. The big, huge, general-purpose battleships that do everything for everyone are probably not as likely unless some clever whippersnapper comes up with a technological advance that we hadn't yet thought of. And your second question? Yeah. Yeah, back at the beginning of my talk. Radio, optical, and X-rays. Yeah, so does James Webb only basically do infrared and the tail end of the optical? Yeah, just that, not the microwaves, not X-rays. Here's the deal for electromagnetic waves. They're all qualitatively the same thing. They have different wavelengths and thus frequencies, but the detection techniques are all over the map. In part because, for example, X-rays travel quite easily through a lot of stuff, including like flesh and stuff, not so easily through bones. But you can focus X-rays with a mirror not with the X-rays coming in perpendicular to the mirror the way the optical light did, but if it comes in at a glancing angle, then it turns out you can focus the X-rays onto the focal plane and stuff. And so there's the Chandra X-ray Observatory, which is also being hit with budget cuts now, really badly. So it's got a nested set of things. And then gamma ray detectors, well, those are things that bonk you in the head. They're so high energy, the photons, like a baseball, although, you know, any single one probably would just go through your head is my guess. But the energy is like that of a rapidly pitched baseball. And so those are gamma ray detectors. And then radio waves, oh man, each photon has such a low energy that it's very difficult to detect individual radio photons. You really collectively see them as a wave. And you know, they're much more of like you think of a wave with TV and radio and stuff. So you need very different devices to detect these different forms of electromagnetic radiation. And never is it the case that a telescope has all the kinds of detectors on it. The best it can do is a range like Hubble, ultraviolet, and visible, and James Webb, a little bit of the visible and infrared, but not all the way up to the microwaves, which can be thought of as a long form of infrared or a short form of radio, you know. So yeah, it's hard. You build telescopes that can do certain portions of the electromagnetic spectrum, but still it's the case that if you make their parameters, like let's say you have a wide field of view and a narrow field of view, and that wavelength and this wavelength and blah, 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 a spectrum that is spread out a lot versus only a little bit. If you try to be everything to everybody, even within that relatively narrow range of wavelengths, it's going to become enormously expensive. As opposed to Kepler, it was fantastic. There's a detector, it looked at one part of the sky near the constellations Cygnus the Swan and Lyra the Harp, and it monitored 150,000 plus stars, their brightness, like all the time, nonstop. And so you would then see these little dips every once in a while, especially when you added the data together or mathematically took a Fourier transform, then you can see periodic phenomena and stuff. And it was really good at that. And it found thousands of exoplanets and then allowed astronomers to study stellar pulsations and things. So it did have other uses, but it didn't even claim that it would have those other uses. It said, what we're going to do is find exoplanets. And that's what the specifications were designed for. And if it happens to be good for a few other things, great. That's icing on the cake. But we're going to be most efficient at designing it to find exoplanets. Those are the kinds of projects which are not that expensive in the grand scheme of things and can yield tremendous pay dirt. Yes?
Is Elon Musk a whippersnapper?
Is Elon Musk a whippersnapper? I think this lecture is being recorded and so will be available to. Elon Musk is an amazingly creative fellow who's had incredible successes. He has overly ambitious timescales, but how can you argue with his success at using those timescales to motivate a bunch of smart people to work really hard toward a goal? Is he going to be on Mars in 2026 or anyone on Mars in 2026? No. Is there going to be a colony on Mars at 2040 or whatever he said? No. But he has ambitious goals and he gets people to work hard at those things. I have not met him. I also don't agree with all of his preferences and stuff. But he's an amazingly clever fellow who's very ambitious and gets people to work hard and achieve some great things. And he's the wealthiest person in the world as a result. So, but he's a middle-aged whippersnapper.
We only have time for one more question.
One more, yeah, I know. Thank you so much. It's way past, most of our bedtimes and stuff. But I mean, he did a lot of these companies when he was a youngster in his 20s. Yeah. So he was a whippersnapper then, for sure. Now he's a middle-aged whippersnapper. Who wants to have the final word in terms of a question? And if not, then we can just end early. Oh, well, one more. Okay.
I do have a question.
Sure.
For a long time, amateur astronomers were able to make contributions to the field
For a long time, amateur astronomers were able to make contributions to the field. Is that changing? Two parts to that question. First of all, yeah, amateur astronomers have discovered comets and all this kind of stuff, and it's not like you can do anything useful with your backyard particle accelerator. All the low-energy particles have been found. It might be fun to have a backyard particle accelerator or a science fair project, but you're not going to do anything. But finding variable stars or comets or asteroids that might even hit us, astronomy has been fantastic in that sense. And I would say that citizen science, in some ways, has become easier in astronomy in this day and age, because now there are all these affordable telescopes. I'm particularly fond of the Unistellar brand and the EV scope. I have one. For a couple of $1,000, you get this telescope that points anywhere you want. There are 1,000 other amateur astronomers who are using these things. Professional astronomers tell those amateurs, here's a star where there's an exoplanet that's going to be transiting tonight. If you all follow it, you'll get some data that will be useful for us, and you might even be involved in a publication, right? That's one way in which Unistellar has set themselves apart from some of its competitors. Some of the competing telescopes are very, very good indeed, but I think Unistellar has the biggest cadre of citizen scientists, so to speak. And I'll tell you a funny story, where a year ago in May, so May of 2023, I was doing a public star party with my own Unistellar. And I looked at M101, the Whirlpool not the Whirlpool, that's M51, the Pinwheel galaxy. And there it was, kind of nice. And the next afternoon, I get a telegram that a Japanese amateur astronomer who's very serious, his name is Itagaki, he's found 170 exploding stars by taking pictures of different galaxies and comparing the new pictures with the old pictures. And he found an exploding star in the Pinwheel galaxy. And I said, well, wait a minute. I looked at that thing last night in my public star party, and the Unistellar saves the data. And I'm like, 10 time zones away from Japan, so maybe I caught it earlier. I looked at the data, and sure enough, there it was. I can't claim to have discovered it. Itagaki discovered it, but I had an earlier data point. We then contacted a whole bunch of amateur astronomers in the US, but I was in California, so there are earlier time zones here on the East Coast, and amateurs elsewhere worldwide, and said anyone who took a picture of the pinwheel that night, May 18th, send us the data. And so what we did is a couple of professionals and myself put together all the data from like 100 or 120 or so of these Unistellar users, and we published a little 2-page paper showing the light curve, brightness versus time, in the first 24 hours of the explosion of this star. And well before, the earliest data points, mine wasn't the earliest because the East Coast got darker sooner than in California. I had one of the earlier data points, but not by any means the earliest one. But by banding all these data together, we showed the light curve on the rise. And, it's not a Nobel Prize-winning discovery, but that's okay. Very few of them are. But these 100 citizen scientists were listed as co-authors on a peer-reviewed scientific paper. And they were happy as clams, And we were very happy to work with them because we weren't pointing any of the big gun telescopes like Keck or whatever, Palomar, at this particular galaxy that night, or certainly not continuously that night. So yeah, there's a lot of room for citizen science still. Although indeed, the all-sky surveys are typically finding many or most of the exploding stars. There was a fellow, Tim Puckett, who would find lots and lots of exploding stars. He had a gang of astronomers all over the place that would take pictures of galaxies. And now the odds are that one of these big surveys, like the Zwicky Transient Facility at Palomar Observatory, will find it earlier. Indeed, I ran a telescope, I still do, at Lick Observatory for a decade, 1998 through 2008. We found more exploding stars that are relatively nearby, within a couple of 100 million light years, than all other groups combined worldwide. That was our glory decade. Then Palomar Transient Factory and other wider field surveys came online, and we couldn't compete anymore. So I tell my students, evolve or go extinct. We had to pivot. And now we do follow-up observations mostly of supernovae that these big surveys discover. And in the age of the Rubin telescope, there's going to be 10,000 of them a night, maybe even more, right? Federica is involved in being the lead of finding, and classifying these damn things. How are we going to follow most of them? That's what I'm, yeah, like most of them are going to be faint. And so, but anyway, we'll talk about that offline. But there's going to be so many of these things from the Vera Rubin telescope and its large survey of space and time, LSST, that these little telescopes looking around on individual galaxies, it's not that worthwhile. Yes, you might get lucky and find one on the rise before the Rubin telescope found it, or the Palomar Transient, Zwicky Transient Facility, whatever. But I felt it wasn't a good use of our time, and so we're spending more of our time on this little microscopic telescope. I have just a 3/4 meter telescope to do follow-up observations. And so in that spirit, some of the citizen science has gone away, but other citizen science has grown. There's the Zooniverse, where amateur astronomers look at all these images taken by all these wide field surveys, and they classify galaxies, certain types of spirals, ellipticals, weirdly shaped galaxies, and anyone can participate in that, even if you don't have your own telescope, right? But the telescopes now are reasonably inexpensive. I mean, the whole thing is $2,500, and that includes the detector and a pretty big mirror and all the software, et cetera, et cetera. Okay, well listen, thank you so much for sticking around, and you can watch the debate online or something like that, but thanks so much.